Go all the way to the top and then work our way down. First one I want to look at. 9 and 10. Let's see. I got to dodge the boxes again today. Number 9. At 1 atmosphere, liquid water is heated above 100 degrees. So we're given the pressure, the atmospheric pressure at this time for this experiment is 1 atmosphere. And now we're heating above 100 degrees. So temperature is actually greater than 100 degrees. Let's see. Delta S of surroundings for this process would be what? Okay. If we look at this in terms of system versus surroundings, that's the best way to set up a picture. If the system is water, right? Water is the system. Liquid water. And the question is, what is the delta S for surroundings? All right. How do I approach this? Okay. In order to increase the temperature here above 100 degrees, we have to transfer heat into the system from the surroundings. So this implies that the disorder of the surroundings is decreasing and the disorder of the system is increasing. So we should expect a change here that's positive and consequently a change here that's negative. Okay. Now let me see if that's the way I answered it in work problems. Oh, in work problems we use the formula. We use this formula. Negative delta H over T. So does that even work? Yeah, that works. This is the delta H is positive because it's endothermic process. And this is actually the delta H of the system. So if this one's positive and that makes it negative, and this has to be negative. So either way you look at it, you should get the right answer. Let's see. How about 10? Oh, okay. So the question for 10 looks at the delta S for the universe. Now, I'm not sure if they're using the universe in terms of our isolated system surroundings, or if they're actually talking about the universe. Because if you think of delta S for the universe, it's always positive. That's the second law of thermodynamics. But what would it be if we considered this one? It's above the boiling point, so we can't say that they're equal. Right? This would be 0 if it were at the boiling point. That's it. The sign-in sheet's right here. We're also in let's see, you need handouts. See, this is 2. Lab. That's next week. That's next week. And I noticed I hadn't given you guys version 1 and 2. I gave you 2 with the word problem, but I just printed out for one. So that's the one we're on right now. So if this is delta S is positive here and this is negative here, then the total of the two should mean that this one is more positive than that one and it's negative. So the best way to answer this one, I think, is just to take them at their word. If they say delta S universe, that means the universe. And it's always greater than 0. That's axiomatic, so to speak. How about 11? Okay. I'm going to take as much time as needed to do this review. So if I ride over into the lab time too much, then we may just ditch this lab. I mean, it's a fun lab to do, but it does take some time to build the battery before you can even test it. Okay, number 11. Oh, by the way, I should put up here, this is version 1, because we're going to go to version 2 in a minute. Which of the following is true? Okay. By spontaneous, we mean that the reaction or process will always proceed to the right as written, even if very slowly. Increasing the temperature may speed up the reaction, but it does not affect the spontaneity. That's a little too nebulous for me. Spontaneous means that the reaction will always proceed to the right as written. Yeah, okay, that's spontaneous, even if very slowly. Increasing the temperature may speed up the reaction, but it doesn't affect the spontaneity of the reaction. Oh, it can affect the spontaneity of the reaction. Yeah, it can affect the spontaneity because we know that delta S, for the surroundings at least, and this we can relate this to the system, is equal to minus delta H over T, and the T has a bearing on the entropy, right? So the T can affect the spontaneity. Yeah. Okay. B. That was A. A doesn't make me happy, so let's move to B. By spontaneous, we mean that the reaction or process will always proceed to the left as written. Now, we can mark that one out. As written, we're saying spontaneous is always to the right. Now, if we say it's non-spontaneous to the right, that means it's spontaneous to the left. Right there, flip side of the coin. So B's out. By spontaneous, we mean that the reaction or process will always proceed to the left as written. Nope. So both B and C are wrong because they go the wrong direction. How about D? By spontaneous, we mean that the reaction or process will always proceed to the right. Yep. So far, D's good. What else does it say? Even if very slowly, increasing the temperature may speed up the reaction, and it generally affects the spontaneity of the reaction. Yes, it does. Yeah. Changing the temperature does affect the spontaneity of the reaction based upon this relationship. Or you could go to Gibbs free energy. Right? Right? If we change the temperature, it's going to change the total value here that's in Gibbs is spontaneous only when it's negative. So temperature does have a bearing on spontaneity. That was number 11. Let's see who's next. Let's skip a few. It's not that they're not important, it's just we don't have time to do all of them. Okay, here we go. 34. Right. 34. For the following reaction, carbon dioxide and water yields methane and oxygen. Carbon dioxide and water yields methane and oxygen. And 2 and 2. 2. Delta H is 803 kilojoules. So the delta H for this reaction, under standard conditions, what did I say? 803 kilojoules. Okay. Which of the following will increase K? Increase K. Get my bearings. Okay. We don't actually have to write the K for this one, because if we're going to use this linear description of the equation, my mind's negative delta H 0 over S. Oh, R, excuse me. R, and then 1 over T, and then plus delta S over R. Okay. Remember this one when if you determine K at different temperatures, if you plot this as the x-axis and this is the y-axis. Right, so x is 1 over T, and this is log K. This is going to give you a negative slope. And the slope is negative delta H 0 over R. So, what's the question again? Which of the following will increase K? All right, so we got choices here. What's our first choice? Decrease the number of moles of methane. Decreasing moles here, as long as the temperature is constant, decreasing the values of any one of these will not change K. Right? K is constant for temperature. Now you can change the equilibrium position by changing the values here, but K is always a constant. Right? So that doesn't fly. Increase the volume of the system. Well, increasing the volume will invoke Le Chatelier's principle, right? Because we do have gases here. And they're not, let's see. No, it won't even work there, right? They're all gases, but you got 3 moles on this side and 3 moles on that side. So it won't even change the equilibrium position because you got the same number of moles on both sides. So the volume is out also. Increase the temperature of the system. All right, what happens if we increase the temperature? Increase temperature. Well, let's see. If we increase the temperature, then this will decrease. This is the reciprocal of temperature. Right? So if this increases, that means this value goes back that direction. So we're moving this way, right? So if we were here and we increase the temperature, we might end up here. Right? So that's a change from here to here of log K. Right? So if we increase log K, does that mean that K also increases? Yeah. So C is the correct answer. Let's see. Do I need to keep any of this up here? No. Okay. 36. All right. Uh-oh. Yes, that one. All right, 36. Okay. Consider the gas phase reaction NO plus 1/2 O2. Yields what? NO2. Okay. And it says delta H0 is equal to what? Minus 56.91. Minus 56.91 kilojoules. It also tells us the K. K was 1.46 times 10 to the 6th at 25 degrees C. Okay, that's everything that's given. Now what's the question? What would be the effect on the amount of NO present of compressing the equilibrium system to a smaller volume? Effect on the amount of NO if we compress while keeping the temperature constant. Okay, so these are all gases. We know that. So we've got 1 mole over here and 1.5 moles on this side. So if we compress the system, it's going to try to make fewer moles of gas total. Right, so it's going to have to shift this side, which means that there'll be fewer moles of NO. That the moles of NO will decrease, which is B. So we didn't need all that other stuff. My guess is that this problem belongs to these conditions are used for several different problems. So we may see that again, depending on the question. In which case I'll have to write all that stuff up there again. Let's see. Ooh, we're skipping a bunch. Here we go. 46. Okay. Given the following data, calculate the normal boiling point for formic acid. The normal boiling point. Okay. All right. So the reaction that we're looking at is formic acid going from liquid to gas. Okay. And if it's at the boiling point, right, if we're at the boiling point, then the delta S for surroundings equals the delta S for system. That's in magnitude. I should write it this way, because when you add them both together, that's the total value. Delta S system equals delta S total. And at equilibrium, this value is 0. So these are equal in magnitude, but opposite in sign. Okay. And we know that this one, surroundings, equals negative delta H over T. So that means delta S system at the boiling point is delta H over T. Okay. So what we're getting at is, what is this one? Right? So if we want to find out what this value is, we need to know that one and that one. So what's the delta H for the system? Let's see. Delta H. All right. So we're going to have to calculate it. The delta H of formation for this one and the delta H of formation for that one. Right. We take delta H for this reaction is the delta H for the product minus delta H for the system. Excuse me. What am I thinking of? Reactants. There we go. So the products are gas, minus 363, and then a minus 410. Okay, so that value should be 410, 363. That should be 47 kilojoules. And now we need delta S for the system. And that would be a similar design here, except just substitute S for each one of these. So that would be 251.1 minus 130. Point 0. Okay, is that right? Yeah, that makes sense. The gas has a higher entropy than the liquid. Okay, so that makes sense. By the way, this is in joules. Joules. So that's 251.1 and 130 is 121.1 joules. All right. So what we need is this formula right here, but this should be in joules. Okay. So what is that in joules? 47 times 10 to the third is 4.7 times 10 to the fourth joules. So delta S for the system is equal, excuse me, plug in the numbers. Let's solve it for T first. T equals delta H over delta S. Now we can put in the numbers. So delta H is 4.7 times 10 to the fourth joules. And 121.1. Right. And this value is going to be in K. All right. Let's see. I get 388. Did it ask for K or C? Okay. So minus 273. 115 degrees C. Okay. So the key to this one is it's at the boiling point. That makes these two guys add together to 0. All right, 46. Let's see. Scroll time. 52. I can't get both of them. Yeah, I can. Just barely. I have to move this out of the way. Let's put it where we can see it easy. All right. Oops. $52. All right. So calculate the delta G for water plus oxygen yields hydrogen peroxide at 600 K using the following data. So this is our target equation. Plus 1/2 O2 and H2O2. And we're given temperature at 600 K. 600.1 K. Okay, and then we're given these. Now, why would we need those? Well, if we're going to calculate delta G, we need a relationship for delta G and just a second. Yeah, okay. Yeah, we're given the K's for those. We need to find the K for the reaction, the equilibrium constant, because of this relationship. Equals negative RT log K. All right. So this actually says this delta G. Yeah, it does say delta G0. All right. So delta G0 implies equilibrium. So we have to use this expression, and we got the temperature. We know what R is. We have to find the K value for that reaction, and that's where these other two reactions come in. So the first one is hydrogen plus oxygen. So we got oxygen on this side. So if we have hydrogen plus oxygen equals hydrogen peroxide. So hydrogen plus oxygen yields H2O2. Right? And the Kp equals 2.3 times 10 to the 6th. And this uses partial pressure. Now, is that going to be all right? Can we use partial pressure here? Yeah, I think so. All right. So we need just half of this. Right? We need half of those, unless the second one needs to be flipped. All right, we may have to adjust this one. Let's put the second one up here while I'm here. It needs to be flipped because water's on the product side. Water needs to be on this side. So let's see. water's on this side, and 2 hydrogens and 1 oxygen on the other side. Okay, and the Kp for this one, since we flipped it, we changed the sign, right? 1.8 times 10 to the 37. Okay. No. No, we don't change the sign. That's for delta H. Sorry. Since it's an equilibrium expression, we take the inverse. Right? Because we're putting the reactants in the product place and the product in the reactant place. That means the value had to be flipped. 1.8 times 10 to the 37. Okay. So we've got one of these. That's good. We've got 2 hydrogens here. We got one of these. How are we going to get rid of that hydrogen? Oh. You guys didn't say anything. So now we can take half of this. Okay. And if we take half of that, what does that do to the K? Remember, if you multiply, I think that's right. Yeah. If you multiply an expression by any value, that becomes the power of the new, to calculate the new K. So this would be first the inverse and then to the half power or square root. Okay. All right. So this gives us one of those. It gives us half here. Then this half cancels half of this one and leaves us with a half there. Okay. Yeah. So we got this one, we got that one, and we got this one. And the hydrogen, since there's only one here, that got rid of the hydrogen also. Okay, so we're good. Now we can calculate the K for this new reaction. So first thing we have to do is take the inverse of this one and then the square root of it. So 1.8 exponent 37 inverted there, and then take the square root there. So this one is going to be 2.36 times 10 to the minus 19. And what does this K equal? It equals that K here and times this K. 2.3 exponent 6 times. Okay, so this is 5.42 times 10 to the minus 13. All right. So now we've got a K, we've got the temperature, we know what R is, we can calculate the delta G. So it's negative 8.3415 for the R value. And the T is already in K. And then the K value is 5.42 times 10 to the minus 13. So that gives us a negative value. This is spontaneous. Water and oxygen makes hydrogen peroxide. Who'd have guessed? Under standard conditions, that temperature. Yeah, that's right. Okay. So let me finish the calculation. I got this one in here already. 600.1 and 8.3145. Change the sign in times. So this is a negative 2.70 times 10 to the minus 9. And I'm wondering where I went wrong. Oh, you know where I went wrong, don't you? I forgot this little character right here. Let's try that again. 600, and then take the log of 5.42. Take the natural log of that, and times. Now we get 1.4 times 10 to the 5th. Negative 1.4 times 10 to the 5th. Now what's wrong? Oh, that's joules. Yeah, that's joules. Right, because of the, this is joules per K mole. Right, so that's joules, and the answer is in kilojoules. So this would be 1.4 times 10 to the 2nd kilojoules, or 140 minus 140 kilojoules, or in that neighborhood. 141, that's close. I think there's a rounding error in there. Okay, let's do 53. See if I can melt my brain. Okay. 53. Consider this reaction. 2 NO2s yield N2O4. There's the delta H, there's the delta S in a container at 298 K, which is 25 degrees. N2O4 and NO2 are mixed with initial partial pressures 2.4 atmospheres and 0.42 respectively. Which of the following statements is correct? Some N2O4 will decompose into NO2, some NO2 will dimerize. System is at equilibrium. The final total pressure must be known to answer this question. All right. So in order to know which way the reaction is going to go, we need to calculate the Q for this reaction, because we're given actual values, 2.4 atmospheres and 0.42. So 2NO2 gas yields, right? Yeah. N2O4 gas. Delta H is minus 56.8. Okay. And delta S is minus 175. Joules per K. Right? Yeah. And the temperature in the container is 298. Okay, that's all the given information. Except for the pressures, 2.4 atmospheres, 0.42. See, I want to put them in the right place. 2.4 on this side over here. 2.4 atmospheres, N2O4. If you're not careful, you put it on the wrong side. This is 2.4 atmospheres. And this, and the other side, because it says respectively, N2O4 and NO2, 0.42 atmospheres. There we go. Okay, so I got everything extracted from the problem. We need to calculate let me think. It's easy enough to calculate the Q. All we have to do is ratio these two. Equals 2.4 atmospheres divided by 0.42 atmospheres squared. So I'd go ahead and calculate that one. Squared and then divide. So I get 13.6 for the Q. Calculating the K is a little more difficult. We know the temperature. If we knew delta G, we could calculate the K. But delta G, let's see, delta G is minus RT log K. Minus RT log K. And what we need is the K so that we can compare the Q to it. Right. That'll tell us which direction the reaction is going to move. Right, but we don't have delta G. So here's another way to find delta G, because we have these values right here. Right, delta G equals delta H minus T delta S. Okay. So we could do it two ways. We could calculate this one and then put it in that formula, or the way I did it here was to combine these two and solve it for K. So let's do it one at a time this time, instead of like that. Okay, so we need to calculate delta G first. So delta G equals delta H minus 56.8. And since this is in do we want delta G in kilojoules? That's 56.8. No, we're gonna convert it to joules. So this is minus 56.8 times 10 to the third joules. For the delta H. And then minus temperature, 298. And delta S, we can leave it as is, minus 175 joules per K. This is K. There we go. So this delta G we'll calculate as 298 times 175. This is a negative and that's a negative, so I'm not even going to change the sign. I'll just leave it like it is. So that's 5.22 times 10 to the fourth. And that makes it positive. And then we subtract this one. 56.8 exponent 3 and subtract. So I get joules. Okay. I can't really refer to this because we're doing it in two steps. Okay, now we can take this one and solve it for K. Well, actually, the best we can do is log K. Log K then would be delta G divided by negative RT. So we know delta G is this one, 4.65. Yeah, this is going to work out because our R is in joules. So this is in joules, we're good. Divided by negative 8.3145 and 298. Okay, that's just log K. 8.3145. Divide that in 298. Divide that one. So this is 1.877. And K then would be e to that power, right? Natural log is e. So e to this power is K. There it is. So I get 6.5 is K. All right. If K is equal to 6.5 and Q is equal to 13.6, what does that mean? That means that we've got too much product, right? Because this is too high and that's too low. So it should shift back this way toward NO2. Some N2O4 will decompose into NO2. A is the right answer. Okay, that's a lot of work just for that one little answer. All right, 53. And scroll to the next. Oh no, we already did that. Scroll to this one. Okay, so let's see, 56. We're still in version 1, it looks like. Consider the following system at 25 degrees. PCl3 plus Cl2. PCl3 plus Cl2 yields, I bet it's PCl5. Yep. At 25 degrees, delta H is minus 92.5. Kilojoules. That's 25 degrees. Let's see. Okay. If the temperature of the system is raised, the ratio of the partial pressure of PCl5 to the partial pressure of PCl3 will. All right. What they're saying is the ratio PCl5 to 3. We're looking at this ratio, PCl5 to PCl3. That ratio, what will it do? If temperature is raised, temperature increases. The easiest way to answer this one is to recognize that this one's exothermic. So that means the delta H goes on this side. All right. So if we increase the temperature, right here, we're going to drive the reaction backwards. Decrease this one, increase this one. Decrease, increase. The ratio should decrease. Yeah, B. That's the simplest way to answer that question. $58. Wish they were all that easy. $58. The equilibrium constant Kp for the dissociation reaction of Cl2 to 2Cls was measured as a function of temperature in K. a graph of log K versus 1 over T, all right, for this reaction gives a straight line with a slope of minus 1.65 times 10 to the fourth and an intercept of 14.51. From this data, which of the following statements is true? All right, so if we got Cl2 going to 2Cl, Cl2 going to 2Cl, that's the bond energy. These are both gases? Yeah. How much energy did you have to put in to make that happen? So this is an endothermic reaction. Has to be. I know that much. We plotted log of K and P versus 1 over T, and that gave us a slope of minus 1.651 minus 1.651 times 10 to the fourth, was it? Yeah, an intercept of 14.51. So it intercepts at 14.51. Okay. Which of the following statements is true? The reaction is exothermic. The reaction is that's a lot of blue smoke. Right? I mean, you could deduce it from the graph. 58. You could deduce it from the graph. Yeah. Log Kp equals, I never can remember this formula. Minus delta H over R times 1 over T plus delta S over R. Yeah, we could plug the values in here, or we could say, all right, we want to get at this one right here. So the slope is a negative 1.651 times 10 to the fourth, which is equal to negative delta H over R. Okay. So if we plug in the value for R, 3145, that multiply it times this one. 1.651 exponent 4 and 8.3145. That's a negative 1.37 times 10 to the fifth equals a negative delta H. Right? So delta H, since this is negative, we just change both signs. Delta H is positive, it's endothermic. Right? So we can either prove it by logic or we can prove it by calculation. Right? This has to be endothermic because we're breaking that bond. All right. So 59. I'm putting you to sleep. Oh. $59. The only reason I'm not going to sleep is because I'm up here talking. For a certain process at 300 K, so temperature equals 300 K, right? Delta G is minus 10.4 kilojoules. Delta G minus 10.4 kilojoules. And delta H is, get out of the way, minus 7 kilojoules. Delta H minus 7.0 kilojoules. Okay. Process is carried out reversibly. The amount of useful work that can be performed the amount of useful work that can be performed. So this process is going to give off free energy with this magnitude. It's spontaneous. So we can gather energy from this spontaneous reaction in the form of 10.4 kilojoules. And that's equal to W max. That's what free energy means. Right? So that's the answer right there. Okay, I like that one. I think that's the last one in version 1. Let's see. Is it? Yes. Okay, now we can go to version 2. So I'll stop this share, and then we'll share version 2. Come on, there we go. Is this version 2? Yes. While it's thinking about it, I'll change this part right here. Yeah, there's version 2. Okay, we need to, come on, get that out of the way. There we go. Make it big. Let's give it an even 200. Okay. There we go. So now go down to number 2. It's like a little probability here. A 2-bulb flask contains 5 particles. What's the probability of finding all 5 particles on the left side? We got a 2-bulb flask and 5 particles, A, B, C, D, and E. What's the probability of finding them there? Well, the probabilities can be expressed different ways, but let's see. That's 1. Here's 2. If we look at it, let's try to make this simple. What's the probability of finding A on one side by itself? It can either be here or here, right? So its probability is 1 in 2. Okay. The probability of finding B on either side is 1 in 2. And the same for all of them. 1 in 2, 1 in 2, 1 in 2. So this would be A, B, C, D, and E. But the probability of finding them all in one place together at the same time, right, is multiply those probabilities together, which is 2 to the 5th, or 1/32. Right, and they've got it in percent, right? So percent would be 3.13. This would be times 100. Okay, that's the way you do that. That's probability. Did they? Let's see. How far have you gone? Algebra? They teach this in algebra? Okay. So I'm not telling you something you don't already know. All right. That was 2, 4. The second law of thermodynamics states what? Well, what's the first law of thermodynamics? Delta E for the universe equals 0. Second law, delta S for the universe is always greater than 0. The universe is running down. So the entropy of the universe is increasing. Yep. It's always greater than 0. That's the simplest way to say it. Nine. At 1 atmosphere, liquid water is heated above 100. Oh, we already did this one, didn't we? Oh, delta S for the system for this process. Okay. So we didn't do this. We did one side of the coin. We didn't do this side of the coin. So if we've got our system, surroundings, and the temperature is greater than 100 degrees, right? We're not at the boiling point anymore at 1 atmosphere. We're above. So if we're above, that means we've got to transfer heat in from the surroundings, and we increase entropy here. So that's going to be greater than 0. This is the energy entropy concept. All right, how about 14? Check and see. We've done this, if there's any overlap. For the process, chloroform solid yields chloroform liquid. CH214 solid goes to liquid. CL3. I'm just thinking, is that chloroform? Yeah, that's chloroform. Another way to say it is trichloromethane. Anyway, delta H0 is 9.19. 9.19 kilojoules. To give delta S also, yeah, 43.9. Delta S, 43.9 joules per K. All right, what's the melting point of chloroform? The melting point would be an equilibrium situation. Right? So we're looking at delta S equals delta H over T, because this is for the system. Since we're at equilibrium, at a phase change, you're at equilibrium as far as entropy is concerned. So this one plus the surroundings equals 0. That means all we have to do is change the sign on the surroundings, and this gives us the system expression. What we need to know is, well, we got it right here. We got this value, 43.9 joules per K is system. Delta H, we need to convert to joules. 9.19 times 10 to the third joules divided by temperature. So temperature is going to be this number divided by that number. Yeah, 209. 209 K equals the melting point. Let's see. They want it in degrees C. So minus 273. All right, so that would be 4 and 6 minus 64 degrees C. Okay. Now, starting to concern me for a minute. I mean, I've never seen chloroform solid before, but it has to be pretty cold. I used to use chloroform in operating theaters, right, as an anesthetic, what do you call it when you put you to sleep? Is that an anesthetic? That's an anesthetic, yeah. They use that. They use ether. Right, so you had to have somebody there with a mask, and they were dripping ether in it as you were breathing it in. You had to keep breathing it because otherwise you wake up in the middle of the operation. somebody cutting on your gallbladder, you wake up in the middle. So it was a continuous process. I think when I had my tonsils out, which is the last time that I had a major operation, they used some kind of gas. They just put this mask on me and said, count backwards. So I said, 10, 9. I was gone. I was also 5 years old too. Next thing I knew, I was waking up, getting my sherbet. 20. I think they didn't give you ice cream because it makes phlegm. So sherbet's safer. In which case must a reaction be spontaneous at all temperatures? Okay. This is fairly simple. We have delta G equals delta H minus T delta S. That's Gibbs free energy equation. And we want to know under what conditions is this one always negative? Yeah, spontaneous at all temperatures. The only way that this can be spontaneous at all temperatures is if to be spontaneous at all temperatures, then this one has to be negative and this one has to be positive. Because this negative makes this term negative, this one's negative, makes that one negative. So delta H, how do they express that? Delta H is negative. Here we go. Delta H is negative, delta S is positive. It doesn't matter the temperature. This will always be spontaneous. Okay, 26. See, we just turn that into a 6. When a stable diatomic molecule spontaneously forms from its atoms, what are the signs of delta H, delta S, and delta G? Okay. A stable diatomic molecule spontaneously forms from its atoms. So we got this diatomic molecule spontaneously forms from its atoms. Right? And I assume that we're doing this in gas phase. Otherwise, the delta H, delta S, and delta G don't mean anything. Because if you have to change phase, then you're adding in another complication. All right, so what are the signs of delta H, delta S, and delta G? All right. It can't be that simple. Well, let's see. Delta H, if this is, well, okay, let's do delta G first. They told us it's spontaneous. Right? Spontaneous means this has to be negative. Right? Okay. And these separate atoms have bonded. The only reason that this bond would form is if this one's lower energy than that one. So this one has to give up energy. That means energy is leaving the system. This is exothermic. All right. Okay. And if we look at it in terms of order versus disorder, you've got 2 moles over here, but only 1 on this side. So this is more ordered than that one. Right? So if your order is decreasing, delta S must also be negative. We're going from more disordered to less disordered. That's a negative change. Right? So they're all negative. That's E. All right. let's see here. 31. All right. We got sodium chloride. Oh, they're looking for the KSP for sodium chloride. 31. Sodium chloride. They're looking for the solubility product of sodium chloride. All right, so it's going into sodium aqueous plus chloride aqueous. That's our reaction, I do believe. Yeah. So the KSP, we don't even need to do that. No, we don't have to do the KSP formula. What we need is delta G, because if we're looking for the K, delta G equals minus RT log K. Is that right? It's minus. Yeah. So what we need is temperature. Were we given temperature? Yeah, 25 degrees. T equals 25, which is equal to 298 K. We do need that. We got that. We need delta G. So what's the delta G for this one? Oh, okay. We can calculate it. I calculate the delta G equals these guys, the delta G's for those. For sodium is minus 262. 62. And then chloride is minus 131. And then minus this one. Sodium chloride is minus 383.8. Minus 383.8. And these are all in kilojoules. Okay, so let's find out what that value is. 262. Change the sign. 131 minus, and then 383.8 plus. So I get a minus 92 kilojoules. All right. So now that we have that, we got the temperature, we can calculate K. But that has to be in joules. Minus 92.0 times 10 to the third joules equals minus 8.3145. This is joules per K mole. And then T is 298. And then log K. There we go. So log K is equal to this one divided by that one divided by that one. All right, I need, there we go, adjust that to joules. And then 8.3145, change the sign. Divide, okay. Then divide by 298. And that's equal to 3.713. So K equals E to that power, right? E to 3.713. So here it is. So that's 41.0. 41.0 for K. Hey, there it is. Shazam. Oops. Aggressive here. There we go. Let's mosey on down. Okay, we've only been at an hour and 15 minutes. We might have time for the lab after all. Consider the gas phase reaction. Okay, we did this one before, didn't we? For which delta H equals minus 56.91 and K equals 1.46 times 10 to the 6th. For this system at equilibrium, how will raising the temperature affect the amount of NO present? We did this one already, didn't we? Was it repetitive? Affect the amount of NO will increase. Yeah, we did this one already. We don't need to do this one again. I don't know how that one got marked. Here we go. How about 40? Second law of thermodynamics states that the entropy of the universe increases during a spontaneous process. Yeah, that's good. Energy is conserved. No, energy conserved, that's the first law. C, the heat content of the universe increases during a spontaneous. No, heat is another way of saying energy. So the energy is constant throughout the universe. Can't be, right? So B is the right answer. We don't need to feed that horse anymore. Let's move on to something else. Here we go. 42. A mixture of hydrogen and chlorine remains unreacted until it's exposed to ultraviolet light. Hydrogen gas plus chlorine gas is stable until it encounters UV radiation. Right? And then what does it produce? Well, it produces 2 hydrogen chlorides, obviously. From a burning magnesium strip. All right. If it's only going to be exposed to the ultraviolet radiation, and was it in this class that I burned magnesium? Or was it in the other class? I can't remember. You'd remember it if I did. It's very bright. It creates UV, so you don't want to stare at it. But this magnesium strip is not in the vessel with this stuff. It's only through a vision port or through a clear glass that UV penetrates and provides the activation energy for the reaction. So it's going to be, as progress of the reaction, here we go. So we got reactants. Let's make that a little higher, because I know this is exothermic. There we go. So we got reactants here and products here, and it's got to go like that. And there's your activation energy right there. So that's what the UV radiation is providing. Then the following occurs very rapidly. Okay. Delta G is negative, it's spontaneous. Delta H is negative, it's exothermic. Delta S is negative, which means this is more ordered than this is. All right, which of the following is consistent with this information? The reactants are thermodynamically more stable than the products. Thermodynamically more stable. Yeah, if it's spontaneous, they have to be. Oh, wait a minute. No. Delta S is negative to be more. Yeah, they are more stable. That's right. But is that the only answer? That's the question. Reaction has a small equilibrium constant. We'd have to calculate, use delta G equals negative RT log K. So delta G is minus 45.54, minus 45.54, and this has to be in joules, 10 to the third, equals minus 8.3145 temperature. So give temperature. We have to assume the temperature is room temperature. Log K. Okay, so let's see what the K is. 45 exponent 3, enter. 8.3145 divide into 298 divide. So log K equals 1.82 times 10 to the minus 3, and K equals, did I do that right? That didn't look right. Hold on a second. 45.54 exponent 3 and 8.3145 divide into 298. Yeah. That just didn't look right. This is 8.38 times 10 to the first power. So K is that to the e to that power. There we go. 9.6 times 10 to the 7. K is huge. Right. So B is not the answer. I'm still wondering about A. I think save us some time by cheating. Okay. See, where was I? C's next. Ultraviolet light raises the temperature of the system and makes the reaction more favorable. No, it doesn't change the temperature. It just provides the activation energy in the form of Planck's constant times frequency is equal to energy. Doesn't have to change the temperature at all. It just provides the activation energy. You can do that without changing the temperature. So C's not it. D, the negative value of delta S slows down the reaction. Okay. This is equilibrium. This side and this side. It doesn't say anything about this. Delta S doesn't. It's a thermodynamic process. It's equilibrium. It's not kinetics. Right? So delta S, that statement about delta S is false on its face. It has nothing to do with the speed of the reaction. The reaction is spontaneous, yes, but the reactants are kinetically stable. All right, can we say they're kinetically stable? Yeah, because the statement tells us that this reaction doesn't go until we provide some energy. All right, so this is talking about this part right in here. This value is big enough to keep that reaction from happening until we provide the radiation. So it's kinetically stable, but spontaneous. So E is the best answer out of that group. And let's stay right here. Consider the gas phase reaction. All right. With these values that we gave it before, calculate K for the following reaction at 25 degrees. Okay. We can do this one. I was scratching my brain to see if we had enough information to do this one. Right, this is number 51. And we're starting off with the equation NO plus 1/2 O2 is NO2. NO plus 1/2 O2 equals NO2. Yeah. Delta H is minus 5691. K is 1.46 times 10 to the sixth. At 25. Okay. And we want to calculate the K for the reaction, for the following reaction at 25 degrees. So we're getting at this reaction, 2NO plus O2 yields 2NO2. Okay. This is not as complicated as I thought it would be. Because in order to go from here to here, we multiply this thing by 2, right? That gives us 2 there. Takes out the fraction there, gives us 2 there. So all we've done is multiply this by 2, which changes K now is equal to 1.46 times 10 to the sixth squared. And there it is. 2.13 times 10 to the 12. I was making it harder than it needed to be. That's B. All right, 52. All right, we're given this graph. Do I need to draw that? Yeah, I guess I do. All right. So we've got this graph of data K at different temperatures. So we've got log K here, got 1 over T here. And we've got about halfway over from here is 0.1. And this one is 0.2. Yep. And then we've got 1, 2, 3, 4, 5. Yep. It intersects right here. And it goes from here to there. Okay. Now, what's the question? What's delta S0 for the reaction in joules per mole K? All right, so we need this formula that I never can remember. Log K equals minus delta H0 over R times 1 over T plus delta S0 over R. Okay. If the question it has to do with delta S0, we only need this part right here, which is here, 3. Delta S0 over R equals 3. So delta S0 equals 3 times R, 8.3145, right, which is about 9, in the neighborhood of 9. Oh, no, I'm sorry. No, that should be right. What is the delta S0 for the reaction? Oh, no. It's not 9. 3 times 8 is 24, plus 1 is 25. It's about 25. Right. That works better. All right. Let's see. We're doing on time. If we're okay. You know, I was just thinking, I've scheduled an electrochemistry lab and we haven't even talked about electrochemistry yet. Have you ever had any electrochemistry before? No? I know why I put it here, because we've only got one more week of class left. Let me think about it a few minutes. Do you guys want to do the lab? You're easy. I just put this lab in to any of my classes as a filler. It's end of the semester and things are crunching on other fronts, and I just wanted to make the lab easy, but I don't know. I'm leaning toward canceling this one. Unless you really got your heart set on it, and then we'll do it. Okay. I don't want to rob you of any of those pleasures. 56. I think we would have had time if I hadn't missed out that one day earlier. Then we shifted this way, and we would have been able to get into the electrochemistry before the lab. And as it is, next week we're going to do electrochemistry lecture, and then review for the exam during final week. You're going to have to do viewing the video, right? Because we won't have time to get in a review in class. Those are the breaks. The equilibrium constant K in atmospheres for the dissociation of Cl2 to 2Cl was measured as a function of temperature. A graph of log K versus 1/T for this reaction gives a straight line with a slope of that number and an intercept of that number. The value of delta H for this dissociation. Okay, so which one do we need for the delta H? We need the slope of the line minus delta H over R, correct? 56. Yeah, that's the slope of the line. And the slope is given as minus 1.651 times 10 to the fourth. Right? So that's all the information you need from that problem to solve for delta H. Right? This is negative, so that goes out. And then R times this, so we just say that times 8.3145 should be delta H. And it's endothermic, which makes sense. We're taking Cl2 and breaking the bond. So 1.651 exponent 4 and 8.3145 times. So I get 1.37 times 10 to the fifth. Should be the delta H, and this is positive. This is joules, right? Is the answer in kilojoules? Of course. So 1.37 times 10 squared kilojoules. Is it in standard notation? Of course. 137 kilojoules. So best answer there is B. $57. $57. For a certain process at 300 K, delta G equals minus 12.2 kilojoules, spontaneous. Delta H is minus 7 kilojoules, it's exothermic. If the process is carried out so that no useful work is performed, delta G is. So no useful work is performed. Delta G equals minus 12.2 kilojoules, which means it's spontaneous. This is the maximum amount of work that can be obtained from that process. But they're telling us they carried out the process so that no useful work was performed. All right, so whatever the process is, they just let all that energy go with them. But did that change delta G? No. Delta G is still delta G. I mean, just because we didn't get any work out of it, that's our fault, or that's the researcher's fault. So delta G is still minus 12.2. It's a trick question. Oh, that was 57 for our recording purposes. Oh, that's it. All right, any questions?